So we move on with Dirk Vries. He's a scientist at KWR Water Research Center, and he is a scientist in modeling of a water treatment plant, has many experience in research in combination of Delft University of Technology and Wageningen University.
Thank you, Petra. So I hope you're all awake, because this talk can be quite technical, but I will just highlight some opportunities, but also shortcomings which you could encounter when using these QSAR. So I will talk about QSAR-enabled predictions in water treatment and going from data to mechanisms and vice versa. It's not about the QSAR. I will explain in the next slide what the QSAR really means, but it's really about the predictions of the occurrence of emerging compounds. So we see that contaminants are increasingly found in water sources and even in drinking water. There have been a paper in the United States, and we need an adequate removal by water treatment. But the problem is that it's quite expensive or difficult or laborious to really test for each compound what the removal efficiency is with some water treatment approach. So this is where model predictions can be of great interest to aid with even decision makers for a new water plant, for example. So, what is a QSAR? Basically, these are statistical relationships, and these relationships are really developed a few decades ago in the fields of pharmacology and chemical industries, where really the need was to have a measure of the toxicity of a certain compound to an organism. So that's where the A stands for activity in an organism, but this term quantitative structure-activity relationship is also used for model parameters. So not only the activity, but also model property. And then it's also referred to as quantitative structure or property relation. So the quantitative, this comes from the mining, the data mining, and the statistical procedure to go from a descriptor set. So this is a set of data of compounds where all kinds of properties of a molecule is stored, and you would like to know if you could predict some kind of biological activity, or in our case a property of a model which can relate to a removal efficiency. So this really is the QSAR then. About the QSARs, if you dive into the literature, you find that, for example, for a lot of water treatment case studies, the data sets are quite limited, and this can be a real problem, as we can see in one paper. There's a citation that the model can only be really validated if there's an external validation set. And what this means is that you really have to split your data into a data set for training and a data set for validation to check if your trained QSAR really performs as well for a compound which was not in your training set. Another thing is that for example, for membrane filtration or other kinds of water treatment studies, sometimes the technology is that advanced and that the retention or the removal rate is very, very good. So it's really hard to have a distinction between the removal of one compound and the other. But there are methods to overcome that. And there are also opportunities, as said in the beginning of this talk, because the experimental investigations of thousands of compounds can be really expensive. Also, we could learn something about the data mining approach, which we will show next. But first, to overcome the shortcomings, I would like to just mention a few tackling approaches to have with these QSARs, because you could really have some more confidence in a prediction of such a statistical model by doing residual analysis, so analyzing the error between your model prediction and the few measurements of the compounds you've got, but also to split your data into the training set and your validation set. And in these methods, there are really few powerful algorithms. Another thing to explore is to check your correlation by chance, because you could imagine that if you have a lot of descriptors which you would like to include in your QSAR, for example 10, and you have only a few compounds, then the hitting of a correlation could be very high, and this you will see in the R-squared value, for example. But let me highlight the steps to get such a QSAR for the UV advanced oxidation case. And let me also highlight that there can be really different kind of these statistical models. One kind is that you directly use all the information from chemical compounds and process parameters and also water matrix parameters to collect this and to find the optimal descriptors that can predict your removal of a compound. We call this database because you only consider these descriptors, but you don't add information of chemical reactions or fluids, computational fluid dynamics, or other laws of chemistry or physics. The other way is to have this QSAR only rely on chemical compound properties. And then you could use this, for example, a reaction rate constant inside a process model, which can then predict the degradation of a compound. So this we will refer to as a knowledge-based QSAR. And of course there are also variations of this idea. Well, the application which I would like to use to illustrate is the UV advanced oxidation case. It's about the by UV light and adding hydrogen peroxide, you can degrade some compounds into, you hope, less toxic compounds. There was a talk of my colleague Roberta Hofman earlier this day, and I will only highlight some parameters which I will focus on. So you have this photolysis reaction, but you also have this oxidation, and in this oxidation you have these compound specific parameters, and you also have water matrix parameters and process parameters like the hydrogen peroxide dose. For the photolysis part, you have this combination of two parameters which are both compound specific. And now the thing is that it's quite remarkable that a QSAR doesn't always predict as well as you would like to be. And we will see that in the next few slides. So we have predicted some parameters seen over here. And to get to this QSAR, you need a certain approach of statistical steps. So the first step is to split your data set in a training set and a test set. And you can do that by mechanistic knowledge. So you know, well, maybe we have to split the test set with these compounds, which will be representative for the other compounds. But you could also use clustering techniques, which is done over here by a technique which is called self-organizing maps. Well, I will not go into details, but it's quite intriguing that by this technique you can cluster your data and, for example, choose from each hexagon one compound for your test set and the rest you choose for your training set. And it's intriguing because you see kind of clustering of compounds which by, well, chemical knowledge will could be explained. So this is a challenge for further research, I would say. Then the next step is to choose the optimal set of descriptors for your QSAR, because you generally, if you have like 1,000 of descriptors, then you couldn't use them all for your prediction, because then the variability will be very high and your reliability of your QSAR will be very low. So you can use genetic algorithms or multiple linear regression, and we've used in this case the multiple linear regression approach. And here you see an example of a QSAR. So it's just a linear relationship which relates these molecular properties to, in this case, the radical reaction rate constant of the UV oxidation process. You see here also some statistics, so the coefficient of determination, linear regression coefficient, and the validation statistics over here. And so the next step is, of course, well, how good is my QSAR? Well, here you can see a method to see how this QSAR performs if you plot the test predictions, or your predictions of your test compounds, and also the predictions of your training set, and also plot the confidence bounds. And in this case it goes pretty well. You could also try to calculate what the total model prediction is. So for this case, we've calculated the removal efficiency in a percentage shown over here, and on the basis of only the predictions, so the yellow bars, you can also calculate the error bars. So it looks quite large, but in this case it's quite good, because if we compare it with other QSARs, then the result can be a lot worse. Still, there's improvement to be done here. Another method is to again look at the confidence bounds, and here we've also used some other data here in green. And then you see that some compounds, the reliability can be, well, not that reassuring, but for the rest, it's quite okay. And here again, we've used this calculation for the whole degradation. So not the model parameter, which is predicted by the QSAR, but the whole removal degradation. Okay. So what I've said the QSAR predictions are not always reliable. In this case, you can see that the external validation, it should be around 0.6 or higher. And what you can see is that if you use some clustering, then for a certain set of compounds, the prediction or the reliability increases. Same here, but even worse for the other parameter. For the nanofiltration, where we used the black box approach, so you use all the conditions, so process conditions and the water matrix properties as descriptors, then you could have this effect that the error bars or the uncertainty really increase. So to come to the conclusions and outlook, there can still be work done, but it is really encouraging that for some parameters and some treatment technologies, the QSAR can really predict in a high reliability range. But for other technologies, sometimes the process model needs to be improved. I've not shown the knowledge-based QSAR for the nanofiltration technique, but here improvements really could benefit the QSAR prediction. Also, the clustering, what you've seen in one of the steps of the QSAR development, can aid in mechanistic knowledge improvement. And I'd like to conclude that really with statistics and what you've seen in the previous presentations is that there is really a need to gather all this data. And we've done this study for in behalf of the Dutch water supply utilities, but in this case you need hundreds of compounds and also some measurements to really train and test this approach, and then it's beneficial to collaborate. So I invite you all to come if you're interested in this method and setup of a database toolbox. Okay, thank you very much.
Thank you, Dirk. Any questions?
Ignas Worm, PWN. In how specific is the QSAR result that you have for the UV peroxide installation that you use? Let's say for the reactor design or the number of lamps, or if you take another reactor or other lamps, are the QSAR still valid, or do you need to redo a large part of the work?
Well, in this case, we've examined only for the low pressure lamp case, and then we got some good results for the OI radical rate constant, but for other constants it was really more difficult, or you have to apply more clustering. For other type of lamps, still a lot of work needs to be done for the knowledge-based QSARs. For the black-based QSARs, we found some peculiarity with the error bars, so there's also some uncertainty left in these predictions. So there's still a lot of opportunity to do research there. Yeah.
Okay. Any other questions?